Hello students, I welcome you in today's session of physics. And in physics, you know very well, we were discussing a topic which is called semiconductors and junction diodes. So in this chapter, we had already covered most of the topics, and now today we will are going to discuss the photodiodes. You can see here, this is the topic photodiode. So a photodiode is a reverse bias p-n junction made from a photosensitive semiconductor. The junction is embedded in a clear plastic. Clear? So the upper surfaces across the junction is open to light while the remaining sides of the plastic are painted black and enclosed in a metallic case. Clear? The entire unit is extremely small, of the order of 0.1 inch size. The circuit is shown in the figure. This is the circuit for the PN junction, photodiode. The circuit is shown in the figure. When no light is falling on the junction and the reverse bias is of the order of few tenths of a volt, an almost constant small current, that is microampere, is obtained. So this dark current is the reverse saturation current due to the thermally generated minority carriers. Fine. Electrons in the p region and holes in the n region. So when light of appropriate frequency is made incident on the junction, additional electron hole pair are created near the junction. Fine. So these light generated minority carriers cross the reverse bias junction and contribute to the reverse current due to thermally generated carriers. Therefore, the current in the circuit increases. Uh, So this is called the photoconductive current, varies almost linearly with the incident light flux. Here you can see this is the figure. Now we will discuss about what is the construction. So this is the construction of the photodiode. So a photodiode consists of a p-n junction embedded in a clear plastic capsule as shown in the figure. So light is allowed to fall upon one surfaces across the junction. The remaining sides of the plastic capsule are either painted black or enclosed in a metallic case. Clear? Now the entire unit is extremely small, of the order of 0.1 inch size. Fine. Now you can see here the voltage ampere characteristics. In the absence of illumination, the reverse saturation current, that is dark current, in a p-n junction diode is proportional to the concentration of the thermally generated minority carriers and is denoted by ID. So when the reverse bias junction is illuminated, the number of newly created electron hole pair is proportional to the number of incident photons. Now the total reverse current, you can write it IS plus ID, where IS is the short circuit current which is proportional to the light intensity. This is the figure for the photodiode. So with any bias, you can write it, the dark current is given by ID equals to I naught I minus V upon ni beta t. This is important equation, so just remember, for where n is equals to 1 for germanium and 2 for silicon, and Vt is the volt equivalent of temperature. So hence the volt ampere characteristic of a photodiode is given by this equation. Now here you can see this is the figure number 16, and what the figure tells about, it represents the volt ampere characteristics curve for three different values of illumination for a germanium photodiode. So only the curve representing the dark current passes through the origin, so it may be seen that the current increases with increase in illumination for a given reverse voltage. Thus the reverse current can be changed by changing the illumination. Clear? Now we will talk about the uses. So if we talk about uses, the p-n junction diode can operate at frequencies of the order of 1 megahertz, in contrast to the slow bulk type photoconductor, which is limited to a frequency range from 1000 to 500,000 hertz. So hence the photodiodes are extensively used in a high speed reading of computers, punch cards, light detection system, light operated switches, counting objects, interpreting a light beam, etc. Clear? Now we will come to what is the junction diodes. It's a solar cells. So third one, a solar cells is a junction diode that converts solar energy directly into electrical energy and is based on the photovoltaic effect. It consists of a shallow p-n junction which is formed at a small distances below the surface of the silicon crystal. There is an ohmic contact at the top in the form of comb-like structure. You can see here, this is the figure for the solar cells. Fine. Which convert about 7% of the silicon area, and an ohmic contact at the bottom which covers the entire bottom area. So the top carries an anti-reflection coating. When sunlight falls on the top surface, it is absorbed mostly within a small distances below the surface where the p-n junction is located. So each absorbed light photo creates an electron and a hole. An electron in the valence band moves up to the conduction band, leaving holes in the valence band. So the built-in internal electric field forces the electron towards the N region and the holes toward the P region. Fine. So the two sides of the junction thus become positively charged, and so a voltage is generated across the circuit. The metallic comb-like structure prevents undue increase of the internal resistance of the cell because of the thinness of n-type silicon crystal layers. Now, solar cells are used in space vehicles for charging batteries in daytime and then taking electric power from them during the night. And this is the figure. There is an n-type layer and this is the p-type substrate. Fine. Now you can see this is the Zener diode. So it is a special type of semiconductor diode named after its inventor, Zener. So it is designed to operate under reverse bias in the breakdown region. This is the most important property of the Zener diode, that is work in the reverse bias in the breakdown region. Zener diode is fabricated by heavily doping both p and n sides of the junction. So due to this, thickness of the depletion region is reduced to less than 1 micrometer. This is the figure for the Zener diode, which in turn increases the potential gradient of the junction to extremely high value. For example, by applying 3 volt, the potential gradient or electric field applied at the junction will be E is equals to V by L. You can easily find out this. Silicon is preferred over germanium for this purpose because of high temperature and current stability. So the symbol for the Zener diode, like this is the symbol. Clear? And this is the voltage characteristic of a Zener diode. This is also the important one. What is the voltage current characteristics? So we know that the reverse current is due to the flow of minority charge carriers. Fine. That is due to the flow of electrons from the p side to the n side and due to the flow of holes from n side to the p side. So further, with increase in the reverse voltage, the potential gradient, that is the electric field intensity at the junction, becomes significant, and at a reverse bias voltage Vr is equals to Vz. It is strong enough to pull valence electron from the host atoms on the p sides, which are accelerated to the n sides. So this is why reverse current is very sharp at the breakdown. The characteristics curve for the Zener diode in breakdown region shown in the figure number 19, you can see here with the graph. Now come to the uses of Zener diode. The Zener diode finds numerous applications in electronics, but mainly it is used as a voltage stabilizer or a voltage regulator. Clear? Now we will talk about Zener diode as a voltage regulator. So here you can see this is the figure of the Zener diode which works as a voltage regulator, and this is the most important property. So Zener diode is a voltage regulator. When Zener diode is used in reverse breakdown region, the voltage across it remains practically constant, equal to the breakdown voltage, which is Vz. So for a large change in the reverse current, clear? What is the working? So in the figure number 20, V input is unregulated input DC voltage whose fluctuation are to be regulated. So for this, Zener diode is connected in reverse bias across a fluctuating DC input voltage Vm through a series resistance capital R. Fine. So if the input voltage increases, the current through the R and the Zener diode also increases. This increases the voltage drop across R without any change in the voltage across the Zener diode. So this is because in the breakdown region, Zener voltage remains constant, even the current in the Zener diode changes. So similarly, if the input voltage decreases, the current and hence the voltage across the R decreases without any change in the voltage of the Zener diode. Clear? So when V input changes, I and IR drops changes in such a way to keep V output equals to how much? Vz, always under the condition. So we can write here V input equals to how much? A multiple of current and resistance plus the Zener voltage. So with the help of this equation we can find out Iz plus IL, or you can find out the Zener resistance this much. Clear? So students, as you can see here, this is the end of the chapter, and we will discuss the other chapters in our upcoming lectures. Till that, do study. Thank you class. Thank you very much.